Okay, today I'm going to talk about 8.6, the ratio test. The root test is also in this section, but the root test is not something that we need for the AP test. So this year, we will not cover the root test. Okay, so we'll just be looking at the ratio test. The ratio test is quite nice. It's just really just kind of a matter of doing some computations. But given a series here, an infinite series, we're going to look at the absolute value of the ratio of a sub n plus 1 over a sub n. If that's less than 1, then the series converges. If that is greater than 1, then the series diverges. If it's equal to 1, that actually means the ratio test is inconclusive. So at that point, you're going to have to do another test. And what I'll tell you is more times than not, if you do get a 1, that means a p-series would work, or like a p-series in combination with a limit comparison test, okay? Also, you know, since we are bounding these things in absolute values, going back to the last section, this proves, when I say this thing converges in the context of does it converge absolutely or conditionally, this would be absolute convergence. Absolutely, for both of these, okay? So just something to keep in mind. And then once again, if it's 1, typically that'd be a p-series or a limit comparison test, or possibly a limit comparison test with an alternating series test would be the most common thing, okay? So I'm just gonna do a couple, well, I guess 4 examples, and that's gonna be it. This is very much just doing the computations. That you're gonna find, you know, most people find that this is a really nice test to use. So let's do those examples. Before we get to the examples, I just want to address a couple things we're going to have to work with today. Because of the fact that we're doing this a to the n plus 1, a sub n plus 1 over a to the n, we have to look at some different combinations. For instance, if I had something like 4 to the n plus 1 over 4 to the n, and I think we've seen these things before, these will cancel, and these are the types of things we're going to be looking at. So for instance here, 4 to the n plus 1, I can call 4 to the n times 4 to the first, right? Because of course our rules of exponents, if we have like bases, we multiply things with like bases, we add the exponents. So we're just undoing this. And so this would, if I see this type of expression, this would cancel out and be left with 4. Another thing that comes up here is factorials. Factorials, so this would be like n factorial. Factorials always are going to have this canceling process that we have to become familiar with. So let's be clear. 6 factorial would mean 1 times 2 times 3 times 4 times 5 times 6. So that's what a factorial is. By the way, these get very, very large very quickly. Your calculator does have a button for this. I don't remember what it is off the top of my head. But what happens with factorials, which is kind of interesting, is let's say I did 6 factorial over, let's say 4 factorial. Well, the reality is that all lesser factorials are factors of higher factorials, because any factorial has all the lesser factors. So 1 times 2 times 3 times 3 times 4 times 5 times 6 over, and that'll be 1 times 2 times 3 times 4, right? So what we're going to see is we're going to cancel. So as soon as I see this 6 factorial, realize I can write it as 4 factorial times 5 times 6. So those 4 factorials will cancel, and I'm left with 5 times 6, which is 30. Okay? So quite nice in that regard. Okay? So if I have something like n factorial over n plus 1 factorial, how am I going to write that? So realize this is 1 times 2 times 3 all the way up to n. Okay? This will be 1 times 2 times 3 times all the way up to n, and then n plus 1. So what's going to happen here is, first of all, we can write this as n factorial over, and then this will be n factorial over n plus 1. So you're going to have to get comfortable with this kind of thing. So this will cancel, and this is left with 1 over n plus 1. Let's do one more, and then we'll get to the examples today. This is really kind of the crux of a lot of the problems we're going to see So it's important we understand how this works. So the last one I'll do before we get into examples is, let's say I have n plus 1 factorial over, let's say, n minus 1 factorial. What's that going to look like? So, I could write these out again, but what I want to realize is the lesser factorial, I'll just leave alone. That's going to be n minus 1. This n plus 1 will have all the preceding factorials. So that means that it's going to have 1 times 2 times 3, all the way up to n minus 1, and then n plus 1, right? So lesser factorials will always cancel with higher factorials, always. So this will be left with, so essentially this is going to be, this is n minus 1 factorial, so this will be n minus 1 factorial times n plus 1 over n minus 1 factorial. So those cancel, so we're left with n times n plus 1, and that is that thing simplified. All right, so let's get into our examples here. Okay. I want to point out that, one of the things you're going to start to see is ratio test works quite frequently. As soon as I see a factorial, I'm typically going with ratio test. Also, a combination of factorials with the exponentials. These are very, very typical ratio test things. Okay, so what I'm going to do here is, first of all, I think it's a good idea to label these. So I'm going to label it a sub n, which is equal to 4n plus 1 over n minus 1 factorial. And the reason why is you have to clearly show this as a ratio. So when I set this up, once I have this labeled, I can just write limit as n goes to infinity of 4 to the n plus 1. If I plug n plus 1 into there, that's going to be n plus 1, so that'll be n plus 2. And then here, if I plug n plus 1, oh, I'm sorry, I skipped what I was saying. Okay, so the ratio, so this is a sub n, so what we're looking at is a sub n plus 1 over a sub n, and we're taking the absolute value of this. So this is absolute convergence, as I talked about before. So this will be the limit as n goes to infinity, n plus 1 goes in, so that's going to be 4n plus 2. And then if I plug n plus 1 in here, it'll be n plus 1 minus 1, so this is just going to be n factorial. Okay, so this is my a to the n plus 1 term. Now I'm going to put that over a to the n, so I'm going to be dividing by this. However, I'm going to have a fraction over a fraction. So instead of writing this as a complex fraction, what I'm going to do is I'm going to multiply by the reciprocal of the a sub n, right? It's going to do the same thing for us. And so the great thing about labeling it this way is what you're going to see is now I'm going to do all sorts of canceling. As long as we have this thing written, we're typically going to point for that, typically, almost always. And then this, when I do the canceling, I can just basically ignore. So what's going to happen here, as I showed you before we started doing these examples, 4 to the n plus 2, I can write as 4 to the nth times 4 squared. And then this, I can write as 4 to the nth times 4. Right? So what's going to happen is the 4 to the nth will cancel. The 1 of the 4's here, so this is just going to leave me with 4. Okay? And so you get this kind of like canceling thing. That's why it's important to label this. Now the factorials, as I showed you before, lesser factorials show up in higher factorials, so I can rewrite this as n minus 1 factorial times n. So the n minus 1 factorial cancels, that's 1. And then this cancels with this, leaving us with n. So what I'm left with is the limit as n goes to infinity of 4 over n. And remember, we're doing a limit as n goes to infinity. 4 over n, that goes to 0. Okay? Well, what are we looking for? We're looking at this L value. Is that L value less than 1, greater than 1, or is it equal to 1? It is clearly less than 1. That is it. I am done. So this is very much just doing the computation. So this converges by, and that is ratio test. And that is how that works. Okay. Let's look at a couple more examples. So once again, ratio test, the first thing I want you to do, really get in the habit of doing this. We're going to label our a sub n. That is going to save you a lot of trouble. Typically, if you don't do that, you're going to lose some points. So the limit as n goes to infinity, absolute value of a to the n plus 1, Yeah, and just doing that is going to get you a point. And pretty much every rubric I've seen with this stuff. So the limit as n goes to infinity, the absolute value, now the n plus 1, so this will be n plus 1. This will be 5 to the n plus 1 over 3 to the, if I plug n plus 1 in there, that's going to give me n plus 2 times, and then we're going to multiply by the reciprocal. So this will be 3 to the n plus 1 over, and then n times 5 to the n. Okay, so same game as before. Now, 5 to the n plus 1 and 5, that will give me 5 here. Okay, now the 3, we can call this 3 to the n times 3 to the first. This we can call 3 to the n times 3 squared. So the 3 to the n's will cancel. This 1, 3 will cancel, and leave us with 1 for this, and this will leave us with 3. Now all we're left with is n plus 1 to n. And what I want you to understand is as soon as I see this type of thing, right, I know that this is just going to equal 1 for large numbers, because we're playing that game where we're looking at the coefficients, they're the same strength. So these will cancel outright, giving us 1. So what am I left with here? I'm left with 5 in the numerator, and I'm left with 3 in the denominator. So 5/3, that's greater than 1, so this diverges by, and then that's ratio test. Okay. Let's do a few more examples. Oh, by the way, at this point, since we're talking about factorials, you know, most of the factorials are easy to figure out. That's 1 times 1, or just 1. 2 factorial is 1 times 2, that's 2. 3 factorial is equal to 6. 1 times 2 times 3. The thing about the factorials is these are patterns you're going to see quite a lot. It's good, you know, just like your squares and things like that if you do memorize them. One that's kind of tricky is 0 factorial, and you just have to accept that 0 factorial is 1, and that's just by definition. Just like if I do 5 to the 0, I get 1. 0 factorial is 1. Okay, so now that I stated that, not that that's an issue here, but at some point if you see a 0 factorial, that isn't equal to 0. So a sub n square root of 5. Why am I doing square root of 5? Oh, maybe because there's a 5 up there. So square root of n, always label these. You know, even in your homework, it gets kind of redundant. It's just such a good habit. So we're doing the limit as n goes to infinity, absolute value of a sub n plus 1 over a sub n. So that's equal to the limit as n goes to infinity, square root n plus 1 over n plus 2 factorial times now the reciprocal. And just like I was saying before with the x over x, these things will cancel outright. So this will be 1. This will be 1. And then this, keep in mind, n plus 2 factorial I can write as n plus 1 factorial times the quantity n plus 2. So this will cancel, and we're left with just the n plus 2. So this is equal to the limit as n goes to infinity of 1 over n plus 2. That goes to 0. That is less than 1. So this converges by ratio test. Okay, one last example, and this one I want to show you an example where the ratio test is inconclusive, and I'll talk about what that means. Okay, last example, and we're going to see what it looks like when ratio test is inconclusive and what we're going to do in that situation. So let's go through this. The limit as n goes to infinity, and the absolute value of a sub n plus 1 over a sub n is equal to the limit as n goes to infinity, square root of n plus 2 over 2 n plus 1. So this is actually equal to 2n plus 2. We got to make sure we distribute this. So that'll be 2n plus 2. Okay, times, and then the reciprocal, 2 over n, and then the square root of n plus 1. So at this point, what you should realize is this is just going to give us 1, because like I said, for large numbers, these have the same strength. We're just looking at coefficients 1 over 1, and 2n over 2n plus 2. Once again, for large numbers, we're just looking at that 2 over 2, so that's 1, and what we get is 1. So as we talked about, if we get 1, that means that the ratio test is inconclusive. So what we realize here is this is something that is going to act like 1 over the square root of n for large numbers. So that's a p-series type thing, comparing it to a p-series. So if if you do happen to stumble across this, and probably at some point most of you will, where you get your ratio test to be inconclusive, you get 1, then that should indicate to you that what we're going to do here is we're going to do p-series or a limit comparison with a p-series, which I'm going to do here. So here's my a sub n. I'm going to compare that to 1 over the square root of n, or 1 over n to the 1/2, okay? So just like we've done before, step 1, the limit as n goes to infinity of a sub n over b sub n is equal to 1/2, okay? And 2, since b sub n, p is equal 1/2, that's less than 1, diverges by p-series. Okay. Then, step 3, that means that our series diverges by limit comparison test. So once again, if you get that inconclusive, it usually means it's going to be a p-series or a p-series with a limit comparison test. If there's an alternator, then it would be, this thing would converge, in this case, by alternating series test. So that's 8.6, really just about doing the computations, kind of very formulaic in that regard. Yeah, the ratio test.